Hey, look at this pencil. It's nearly a Reuleaux triangle, and that means it's nearly got a constant diameter. Let's have a look how that pans out when you put a whole bunch of them in a row and run your hand along. Your hand doesn't go up and down off the table. Your hand stays the same distance from the table, even though they're rolling along, because they have a constant diameter. You'll notice they don't have a constant radius. If it's turned that way going down, there's a long way from the center to the bottom, but that way there's a short way from the center to the bottom. But they have a constant diameter, so it still keeps my hand the same distance off the table. And it is quite satisfying doing this. I'll see you back at the board. So the Reuleaux triangle has a constant diameter, but not a constant radius. Things with a constant diameter are pretty useful, besides being able to get a smooth, flat sort of run along there with a whole bunch of them. They're good as a manhole cover. Look at this square manhole, right, with a nice square cover. It's slightly bigger than it, so it won't fall in unless you turn it and easily pop it in. There's plenty of room there to pop it in. That's no good. A square manhole would be useless. A circular one seems the obvious choice. This is slightly bigger and it will not ever fall in, no matter how. I can try every angle I like. It's not going to go in. So that's a great idea. You're not going to clunk someone who's down there with the manhole cover, or you're not going to drop it in there and have to crawl down and get it. Reuleaux triangle has a constant diameter, so you can use that for a manhole cover as well. Let me draw one up for you. First thing I'm going to do is draw an equilateral triangle, and I'm going to make its side length the same as this. You might like to speed this up because this takes slow time in real time. So the equilateral triangle has that side length just about there. Okay. Same side length. Okay, I just drew up an equilateral triangle, and that equilateral triangle has that side length. Look, this is only rough, but it's giving you the idea of what the Reuleaux triangle looks like or how it's created. So I'm going to draw little arc lengths with that radius now. Starting here, I'll draw an arc length with that radius. And now starting here, with this is the center of my circle, I'm going to draw an arc length with that radius. And now I'm starting here with this as the center of my circle. I'm just going to draw an arc length with that same radius. And I can see that my circle, my original triangle, was a little bit off. But there you go. That blue one, if I'd drawn it accurately, that blue shape is a Reuleaux triangle. It's like a triangle with curved sides. And it has a constant diameter. So from here across the circle, or across the Reuleaux triangle, to any point is this radius here. So it's got a constant diameter of the whole shape. So that thing won't fall into a manhole. Well, if I drew the circle that would fit through those three vertices of that triangle, so say that's the center of such a circle and that's its radius, it would sort of go out there, around down there, and back over there. So there's a bit of a circle drawn through there. Not the best circle, I admit. But if I drew that circle, that could be a manhole cover with the same kind of center as my Reuleaux triangle, but clearly it's bigger than the center, but than the Reuleaux triangle that I've got there. So my question that I'm going to answer now with you is, what is the difference in area between that large, big red circle that has center in the middle of that triangle there, and the Reuleaux triangle, which is this blue-shaped kind of triangle with curvy sides that I drew? And what's the difference in area between the two? And let's only have this one variable in it that we will call R. R can be this length. R is the length of that side of the original triangle, the black triangle that's in the middle that I drew. What's the difference in area? That's what we're going to answer. So we need the area of the Reuleaux triangle that's in there. So how are we going to find the area of the Reuleaux triangle? Well, one way is to do the following. To find the area of 3 different sectors. First sector is the one that I'm outlining now. So I'll make it a bit darker in case you can't see very well, which is likely on this video. That sector there that I just coloured in, I'm going to find the area of that. So I'll just write that down. We're going to find the area of a sector. It's got R like that. And the angle down here for that sector is 60 degrees, or pi on 3 if you're going to use radians type formulas. All right, now you saw that I drew 3 such sectors when I drew this triangle. Right? So instead of that sector, we could consider this sector going down here. Right? That sector there is one of the 3 sectors that I drew. And of course, the other sector that I drew when I drew this shape was this sector out here. That's 3 different sectors that I drew to draw up the shape. And so if I add up all their areas, it's going to be way too much. I agree, because there's the middle triangle was involved in all 3 sectors. So this triangle in the middle here was involved in this sector, and in this sector, and in this sector. So I've overdone it. I only needed to add that area of that triangle in once, but I've added it in 3 times. So you guessed it, I'm going to subtract away, and I'll just give myself a bit more room there. I'm going to subtract away 2 of those triangles. I'll just draw minus a couple of those triangles there, those green shaded triangles. That's what I'm going to subtract away. And they have a radius of a side length of R as well, don't they? All right. So if I add those 3 sectors and take off the 2 triangles, I'll have the area of the Reuleaux triangle, which was originally drawn in blue, but I've sort of drawn all over it now. But I'll have the area of that Reuleaux triangle there. All right. So I'm going to go ahead and I'm going to do that now just quickly. The area of this sector, the entire sector, is a half r squared theta, where theta is in radians. Half r squared theta, where theta is in radians. And so is this one, half r squared theta, where theta is in radians. And so is this one, a half r squared theta, where theta is in radians. This here, we know that that's 60 degrees in there. So that area is a half AB sine C. A half AB sine C. And minus a half AB sine C. It just makes it in. So there are actually, there's the area of the Reuleaux triangle is 3 of these a half r squared pi on 3s minus 2 of the triangles, a half r squared What's sine 60? Sine 60 is root 3 on 2. So this is a half r squared pi, and this here is a half r squared root 3. So I can pull a half r squared out. Yes, I've said a half r's a lot in this. A half r squared, and then that's pi minus root 3. That's the area of the Reuleaux triangle. Now my question was, what's the difference in the area between the big red circle that went around the outside through the vertices and the Reuleaux triangle that I found the area of there? Well, I need to know the radius of this circle here. In other words, how far is it from the center out to one of the vertices of the triangle? Because that's the radius of the circle. Now recall, I'll have to rub this out a little bit here, but recall that the side length of the triangle here was r. The side length of the triangle was r, going across there. That side length is r. And so I can easily find that. If I want to call that capital R, I can easily find that, because let's complete this triangle here. This would also be capital R. It's isosceles. So up in here, this is 120, and down here, this is 30 and 30. So if we peel this triangle off, R, 30, 30, 120, we can use the sine rule to find what that length, capital or uppercase R, is in terms of lowercase r. So uppercase R over sine 30 equals lowercase r over sine 120. So r equals r sine 30 on sine 120 equals r times a half on root 3 on 2. So that's just r on root 3. This radius of the red circle is r on root 3. Well, then we can find the area of the red circle, because it's pi times the radius squared. So I'll just go ahead and find the area of that. I'll keep this area here of the Reuleaux triangle, because we're going to be finding the difference in a tick. So I've got the area here of the circle minus the area of the Reuleaux triangle equals pi times the radius squared, and the radius is r on root 3, and then minus this half r squared pi minus root 3. So I get pi r squared on 3 minus pi r squared on 2 plus root 3 r squared on 2. So that's root 3 r squared on 2 minus pi r squared on 6, because we've got 2 of those on 6 minus 3 of those on 6. And then I can just clean that up now and say that it's equal to r squared into root 3 on 2 minus pi on 6. Now, the full circle is pi r squared. This is this many r squareds. The difference is this many R squareds. In other words, the bit I'm shading in red right now, hold on, just this outside bit, that's what we just found. We found that red bit around the outside. That's that many R squareds. Bearing in mind that the area of the whole circle is pi R squared, which is about 3.14 R squareds, this isn't going to be so huge. It's a certain number of R squareds. I'll put that in the calculator and I'll tell you what that is. 0.34 R squared. That's about 0.34 R squared. About a third of a circle. So you're saving about a third of the area of a circle by going to a Reuleaux triangle if you are making that comparison between those two objects there.